A photoelectron spectrometer uses X-rays in order to eject electrons from an atom, and in this way, we figure out the electron configuration for the atom. So it's not unlike the photoelectric effect, right? Actually, it is the photoelectric effect, right? You put a certain amount of h nu, right, energy into an electron and you move it. So once you hit the threshold frequency, right, a high enough frequency that you're going to beat the energy that the atom's using to hold onto it, if you put in high energy, right, so we're using X-rays, right, using X-rays, and when we remove the electron, right, put in a high energy light, we beat the binding energy. Any extra energy that's left over is the kinetic energy that electron has, right, how fast it's moving off of the atom. So what we can do is set up some sort of detector and measure the kinetic energy that the electron has. So based on how much energy we put in, how much kinetic energy this electron has, we can figure out what the binding energy was, how hard that atom was holding on to that electron. And that's what you get out, that's the readout you get when you're using a photo spectrometer. So here's lithium, right? We've got the inner electrons, right? The core electrons, and we have the outer electron in the 2s, right? Ground state electron configuration for lithium. So the core electrons are the hard ones to take off, right? They're the ones that are less shielded. The electron on the outside, the valence electron, is being blocked from feeling the nucleus, right? Feeling that binding energy by these inner electrons, right? Electron-electron repulsion, right? You're pushing that electron off. So it's going to take less energy to knock this electron off. It's going to have a lower binding energy. So from the detector, what we get is a bump, right? A little bump representing one electron being knocked off of this atom, right? So we had the helium core, right? There's the helium core and the 2s electron right up at the top there. There's the electron configuration for lithium. I zap that 2s electron, I knock it off, and I get a bump at 0.52 megajoules per mole. So that's the binding energy per mole of electron being removed from this lithium, right? At that point, that's removing the electron from the 2s. It's going to cost me more energy to remove electrons from the 1s. Not only that, but I'm going to get a bigger bump, right? I'm removing 2 electrons. So I get a 2 electron bump at 6.26 megajoules for the 1s electrons, right? The less shielded ones. So easy to remove this one, right? And it's a smaller bump, so that represents 1 electron being removed from the 1s, and we get a 2 electron bump here at the 1s, right? So this is the 2s electron being ejected. This bump right here represents the 1s electrons being removed. So I knocked 2 electrons off. And this would be the readout you'd get for lithium, right? This represents the electron configuration. 1 electron in the 2s, 2 electrons in the 1s. All right, and I've made lithium plus. I can take all the electrons off of an atom in this way, right? In nature, lithium only loses 1 because this is the easy one to take off, right? It takes way more energy to start digging those electrons out of that 1s, right? This bump right here. So this is why we don't find a lithium 3 plus. Too much energy in nature to knock those electrons off. But I can do it in the lab with X-rays. So to knock that electron off of hydrogen, right, I get 1 bump, a 1 electron bump at 1.31 megajoules. All right, so hey, this is an unshielded electron. This is hard to knock off. This is why hydrogen doesn't behave like a metal, right? It's more like a halogen. It has such a high binding energy. Helium's going to be even more energy, right? You've got 2 protons holding on to those electrons in the 1s. So you have a much higher binding energy. And you get a bigger bump, right? You're taking 2 electrons off. So hydrogen, 1.13 megajoules. Helium, 2.37 megajoules. And I've got a 2 electron bump, taking those 2 electrons out of the 1s. This was lithium. We did lithium. There's removing the electron from the 2s. There's the bump removing the 2 electrons from the 1s. Again, notice the big jump, right? We've got 3 protons now holding on to those electrons in the 1s. Whereas with helium, we only had 2 protons trying to hold on, right? So easier to remove the electrons from the 1s of helium than trying to dig them out of the 1s of lithium, right? More protons holding. Beryllium, I've got 4 protons, right? So the binding energy in the 2s goes up, right? It gets harder to remove those 2s electrons, and you get a 2 electron bump again. How much energy it takes to knock it off, how many electrons you're knocking off. So 2 electrons being pulled out of the 2s, 2 electrons being pulled out of the 1s. Again, look at how high that binding energy is on the 1s, right, with 4 protons trying to hold those electrons in the 1s. Boron, you get a 1 electron bump out at 0.8 megajoules. All right, so that's the easiest one to knock off. Then we get a 2 electron bump at 1.36, taking electrons out of the 2s. And look at trying to dig those electrons out of the 1s, right? 19.3 megajoules with 5 protons trying to hold on. So it gets harder and harder to dig those inner core electrons out. Well, the core electrons in this case, right? This is the core. Got a helium core here, and we've got 3 outer electrons. So these are the easy ones to take off. This is super hard, right? That's why, we don't remove core electrons. They're unshielded. Too hard to take off. Carbon, right? You get a 2 electron bump out at 1.09, right? That's removing the 2 electrons from the 2p. We get a 2 electron bump at 1.72, removing electrons from the 2s. Again, right, because of its shape, this is a lower potential energy position, right? So it's harder to take electrons out of the 2s than the 2p. And again, core electrons, it keeps going up and up, right? The more protons you put in that nucleus, 6 protons, the harder it is to dig out the core electrons. So core electrons shielding outer electrons from feeling the nucleus. All right, so this is the way the problem would go on the test, right? You'd be given a readout of the photoelectron spectroscope, and you'd have to figure out what atom you're dealing with, right? So identify this atom. All right, so the way I look at this is I've got a little bump way out there at 0.8, right? So it's a 1 electron bump. So looking at this looks like it would be something like out of the 2p, right? Because I've got two electrons at the other 2 bumps that are higher in energy. So since I have 1 electron that's easy to take off, and then I've got 2 electrons that are a little bit harder to take off, those look like 2s electrons to me. And the ones that are really hard, right, would be the core electrons, right? I'd have 2 electrons in the 1s. So 5 electrons total, this looks like boron. And this is the way the test question would go, right? You'd be given the readout, and you'd have to figure out what atom you were dealing with. So it's like a clue, right? Here's your clue. What is this atom? Oh, I've got got 1 bump that looks like a 2p. I've got 2 electrons right at the next bump. Looks like 2s electrons. Oh yeah, and there's the core electrons, right? Those must be the 1s electrons. Boron.